us now discuss about the Doppler effect of light. The apparent change in the frequency of light due to the relative motion between the source of light and the observer is called the Doppler effect. You have already studied about the Doppler effect related to sound waves. Let us recollect the expressions we had derived for the Doppler effect of sound waves. Let Vs be the velocity of the source, Vo be the velocity of the observer. Both these velocities are relative to the medium in which they propagate and act along the line joining them. Also, let nu0 be the frequency of sound when the source and the observer are stationary. Nu be the frequency when the source is in motion and the observer is at rest. And nu dash be the frequency when the observer is in motion and the source is at rest. Then, as for the Doppler effect for sound waves, we have nu is equal to nu0 into 1 minus Vs by V, and nu dash is equal to nu0 into 1 plus Vo by V. Let them be equations 1 and 2. Thus, in the case of sound waves, since the velocities of the source and the observer are relative to the medium in which they propagate, the effect on the frequency when the source moves away from the observer is different from when the observer moves away from the source. But this is not true in the case of Doppler effect for light waves. Let us now understand the reason for this. We know that the speed of an electromagnetic wave is same in any inertial frame of reference. As a consequence, for the purpose of Doppler effect of light, a source of light moving through a medium in which the observer is at rest and an observer moving through that medium with the source at rest are physically identical situations. Hence, we cannot use equations 1 and 2 in case of light waves. The expression for the Doppler effect of light is predicted based on the theory of relativity. The expression is nu is equal to nu0 into square root of C minus V by C plus V. Let this be equation 3. In this expression, C is the speed of light in vacuum and V is the velocity of the source with respect to the observer. V is taken along the line joining the source and the observer. V is positive when the source moves away from the observer and is negative when the source approaches the observer. Equation 3 can be mathematically manipulated as shown to obtain equation 4. If V is very much less than C, then V square by C square is much smaller than 1 in equation 4, and hence it can be neglected to obtain equation 5, where nu is equal to nu0 into 1 minus V by C. Equation 5 can be rewritten as nu minus nu0 whole divided by nu0 is equal to minus of V by C. If the change in the frequency nu minus nu0 is written as delta nu, then the fractional change in the frequency delta nu by nu0 is equal to minus V by C. Doppler effect of light has an important bearing in astronomy. When light emitted by stars is passed through a prism, a spectrum is obtained. In the visible part of this spectrum, lines of different wavelengths along with some intermediary dark lines are present. If a star moving away from us, there is an apparent increase in the wavelengths due to the Doppler effect of light, and hence the whole pattern of the spectrum gets shifted towards longer wavelengths. This is called the red shift. Our universe is continuously expanding. The astronomers have found an experimental proof for this in the red shift. When a star is moving towards the observer, there is an apparent decrease in the wavelengths and the whole pattern of the spectrum gets shifted towards shorter wavelengths. This is called the blue shift. It is important to note that we can measure either the red shift or the blue shift very accurately by comparing the apparent wavelengths of the spectral lines with the known laboratory wavelengths.